Okay, imagine that you have a design project, and the project is to come up with some alternative ways or some novel, innovative ways to heat water for showers. And one of your team members, or maybe you have the idea of that, hey, why couldn't we possibly use a microwave or some type of microwave energy to heat up water, either at the head or down in the basement or some back room where the water would be heated and then it would be transferred into the shower. So we're going to explore that a little bit. I mean, it's really hard to understand if it's a good or bad idea sometimes, unless you've had some kind of analysis, some type of approximation for various parameters for the design. So in this case, we probably want to consider things like how fast can it heat up the water, and also, and maybe even more importantly, is it was one more efficient or less efficient than the others? So in terms of the energy that it takes, so does microwave energy take less energy than what's currently done to heat up water in a shower? So for that, we're going to use a microwave that I actually just went and got from the makerspace here, and I'm going to use a water kettle to represent how water is currently heated in showers, because that's pretty accurate of how hot water is generated in a shower. Typically, a hot water heater in a home will just use electricity, and it will heat up a resistive coil that's in a large tank, and then that water will then go to the pipes to the shower. So we want to compare these two. And so this is just a quick and dirty test. It's a really good way to understand some design options early on, and it's meant to be just very simple experiments. So I'm going to go ahead and just step through the process, and then at the end we can reflect a little bit on it and try to understand some various outcomes. All right, so in order to do this experiment, I'm going to use a kilowatt, which is this device that allows you to measure the power, the electrical power being used by a device by plugging it in. And I'm also going to just use a bottle of water. And I know the amount of water because it's written on there as 500 milliliters. So that's useful. And I'm also going to need to measure the temperature of the water. So the first step here is to put in the spreadsheet the amount of water that I'm using. So as I mentioned, it's 500 milliliters. And since we know the density of water, we can then calculate the mass of the water in this bottle. So I would want to note that in my spreadsheet. The next step is to measure the temperature of the water. I just went and got it out of the faucet. I emptied the bottle of water because it was pretty cold, and then I filled it with more water. And I can see here from this thermometer that it's about 58.5 degrees. So I'm going to go ahead and note that in my spreadsheet. And then I'm going to heat it up in the microwave first. And I'm going to go ahead and heat it for 1 minute. And as it's heating, I'm going to note how much power is being used. So put it in for 1 minute and start. And I'm going to put the watt button here to see how many watts are being used. And it looks like it's actually fairly steady at about 1,500 watts, or 1.5 kilowatts. And it's still staying about the same. It's about 1.5 kilowatts, or 1,500 watts. All right, so I'm going to jot in my spreadsheet that it was 1,500 watts being used. I'm going to take the bottle of water out, and then I'm going to measure the temperature increase after being heated for 1 minute. And it's about 96 degrees Fahrenheit, or 35.4 degrees Celsius. And so the temperature I mentioned earlier was in Fahrenheit. So I'm going to go ahead and put it in Celsius, 35.6. So now I'm going to do the same experiment using this water kettle, which, as I mentioned, is more representative of how water is currently heated in a home. So I went and emptied out the water that I just heated in the microwave and poured in some new water. And so I'm going to want to take the temperature again. So now the temperature is 57.7 degrees, similar to before, or about 14.3 degrees Fahrenheit. So I'm going to go ahead and note that in my spreadsheet. And then I'm going to dump this water. I made sure that this is hasn't been used in a while, so it's kind of cool. So I'm going to dump the water in the kettle. And then I plugged it, the kettle into the kilowatt, just like I did for the microwave. And just like before, I'm going to heat the water for 1 minute. Start the timer for 1 minute.
Your timer is set for 1 minute.
Okay, and while it's heating for this 1 minute, I'm going to look at the wattage being used. So it's using about 1,300 watts, or about 1.3 kilowatts. And the wattage seems to be staying fairly constant. All right, so that's 1 minute. I'm going to go ahead and stop the heat so it went down to 0, and I'm going to mark that it was about 1,300 watts. And then to get the final temperature, I'm going to go ahead and just stick the temperature probe inside, and we see that it's about 50 degrees, 49 point something. And the first entry here was the amount of water that I had in terms of volume, and that I calculated by reading off the 500 milliliters that was written on the side of the water bottle. So you don't really need a fancy measuring device. You can just use either a cup or, in this case, a water bottle that has some already measured amount of volume of water inside. So this is the volume converted from milliliters to meters cubed, which is the units that I need. Then I calculate the mass of the water by taking the density of the water and multiplying it by the volume, and that gives you the mass in kilograms. The initial temperature was 14.7. That I obtained by measuring the water using that MEAT thermometer. And I initially measured it in Fahrenheit, and then I had to convert it to Celsius, which is pretty common. In this case, the thermometer had a nice little converter already on it, but sometimes you just have to convert it using Google or some other approach. The next thing is the 1,500 watts. So that was the power coming from the outlet into the microwave as measured by the kilowatt. So it's basically how much energy is going into the microwave through the electricity. The next was how much time was taken to heat it up, and for both cases we let it heat for 60 seconds. Then I calculated, based on these measurements or recorded values, I calculated the electrical energy in. So this is the energy coming in, and it has different units. It has joules. So what you do to calculate that is you multiply the power times the time. And by definition, that gives you the amount of energy, or joules, because the definition of power is energy per time. So if you multiply by time, you get energy, which has units of joules. Okay, the next thing I recorded was the final temperature. So this is after heating up the water in the microwave. And then the change in temperature was just calculated here by taking the difference between the final and initial temperatures. The energy increase in terms of how much energy went into the water, this is this requires a calculation using what's called the specific heat of water. So basically, it's trying to understand how much energy went into the water based on the difference in temperature that was observed. And the equation is written here off to the side, which is the change in energy is equal to the mass of the water times the specific heat of the water times the change in temperature. So that's essentially what I did. Is I took these values. I took the mass times the specific heat times the change in temperature that was observed, and that gave us a value for how much energy actually went into the water. The final calculation was efficiency. So that basically says how efficient was the microwave at converting electrical energy coming in to actual heat in the water. So to calculate that, you just take the change in energy, which is this cell here. So that's how much the water did change in terms of energy, divided by how much energy was put into the system using electrical energy. And what it showed here is that the microwave was roughly 48% efficient. So I did the exact same thing using the electric kettle as you saw previously, and I just recorded all the values. So it was exactly the same idea of all the different calculations. And what it came out to be is that the electric kettle was about 94% efficient. So in terms of just pure efficiency, you can see here that the electric kettle is very efficient, and the microwave is not efficient. And the reason why is, or reason might be, is that to use a microwave, the microwave actually has multiple steps to convert from electricity to heat. So it's a little beyond the scope of this discussion, but it essentially has to do with energy conversion. And the microwave has to step through basically from electrical energy to a microwave tube that then heats up water. In the case of the electric kettle, it's very direct. It goes electricity directly to heat through a resistor, which is an electronics term, but it's essentially a way to generate heat using electrical current. I mean, that's one way to use it. That's one thing that happens when you pass current through a resistor, is that it generates heat. So just purely based on efficiency, you can see here that the microwave is not the way to go, and the electric kettle works pretty well. It's pretty efficient in terms of generating heat from electrical energy. The other thing to consider is how well the water was able to increase in terms of temperature. So that's kind of a measurement of how fast would the water heat up. And you can see here that even though the electric kettle was using less power, it was able to heat up the temperature quicker. So it actually had a 35-degree temperature difference in that 1 minute, while the microwave only had a little, like a 21-degree increase in time. So that really says that the clear winner is the electric kettle. So from a design perspective, I think these are approximations that can be then taken back to the design team or be part of a discussion that's had that really indicates that probably microwave energy is not a good approach, but it's a lot better to use this quantitative approach in some of these experiments, because you start to learn and understand some of the trade-offs, and it allows you to actually have some more concrete numbers to evaluate and to discuss versus just thinking about it or maybe arguing about something without having this type of information.